It's a great pleasure to invite Trevor Darrell. He's a faculty in CS and departments at UC Berkeley. He's also a faculty director at the PATH Research Center at UC Berkeley. His research has spanned several different topics within computer vision, machine learning, and natural language processing. Recently, his group has focused on developing algorithms which are also tied to explainable and advisable learning. So, Trevor, this is yours. Thank you.
Great, thank you very much. Thanks for that introduction. And it's really wonderful to see such an interest and enthusiasm in explainable AI and such a big turnout today. I think it's a hallmark of the field that this is a topic that's more and more of concern and focus. And today I want to give you our perspective at Berkeley and especially how you can have your cake and eat it too, at least in certain circumstances, by taking techniques from explainable AI and pivoting towards what we call advisable learning. Of course, we're all here, to try and make machine learning and the buzzwords of deep learning and whatnot more explainable and trustworthy. That's an inherent goal that we all have. And these motivation slides, I'm sure everyone in the room has their own version of them if you're coming to this workshop, of how we want to move beyond black box, overly parameterized models that don't expose themselves, don't convey or lend confidence in their predictions. And this is a very historical slide here. This is sort of one of the slides from the original XAI program. And how do you, originally the idea was there's a trade-off between different kinds of models that you have to choose. Do you want models that are interpretable and explainable, or do you want models that work? And I think it's a little bit of a false choice that often was expressed in the field that, and I mean, there are some regimes in which there's a theoretical truth to this statement, but there are also ways you can step outside of that box, as I'll explain in the rest of the talk. Because I think that actually explainable and ultimately advisable models transcend this and allow us to have models that are both performant, interpretable, and even more performant because the explanations themselves become ways that we can teach the system what they should do, or tools for teaching the system what they can do. So our approach has been not to constrain architectures unduly, but instead to use more deep learning to build interpretable deep learning. And there's two different paradigms that we've explored, one based on modularity and one based on justification. I just need to move some things off my screen so I can see everything. Hide panel, hide floating panel. Okay, and then close that thing. Great, now I can actually see my screen. So the first is modularity. And I need to touch my screen so I can, there we go. Modular architectures are imposing structural interpretability, structural explainability on models. And I think you've probably seen examples of this earlier in the workshop. I'm going to refer to salience models in this category. We've also had work on modular neural networks in the past in this category. But it's in contrast or with justification-based models. And those are more storytelling approaches. In the modular approach, we try and constrain an architecture to have some sort of causality or interpretability. In the second, we tell stories, or we have one network that tries to explain or tell stories about another network. We call those justification-based approaches. So let's first take a look at introspective models or causal models. And these are models such as the classic work in salience that's been built over the years, notable methods including LIME, GradCam, and RISE, which of course can provide interpretations of what pixels in an image or what regions in an image were useful for certain explanation. So if you're trying to classify something as a sheep, you'd have one highlighted region of the image, and if you're trying to classify the same image as a cow, you might pick a different, not cow, but it's sort of, you can understand why the model would make that mistake. And these models are important because we would like systems to be not only right for the right reasons. We've argued that such architectures for visualizing the salience or the contribution of different models can allow you to create architectures that can, for example, deal with debiased data sets. So you can see here that an image captioning model, for example, the work that we presented several years ago at XAI4CV, would output a caption that would incorrectly, at least apparently according to this setting, rely on the context, the fact that there's a computer to decide what gendered word to refer to the person in the image with. But if you actually were looking at the person and not looking at the surrounding context of the environment, you would generate perhaps a more correct word here. So this ability to have an interpretation is useful to make these kinds of decisions. And we've recently extended this towards continual learning. I'd like to highlight a paper we published at iClear last year on using explainable AI to improve performance in a continual learning setting and to reduce the effect of catastrophic forgetting. Catastrophic forgetting, as I'm sure most of you know, is this problem in continual learning, where if you have a set of different groups of tasks and you train a single model using conventional fine-tuning approaches, first to learn one group of tasks, then another group of tasks, then another group of tasks, then another group of tasks, the model will often forget the first group of tasks by the time it's done with the last group of tasks. And a common approach to this is called experience replay or remembrance. And so we actually looked to see whether saliency or remembering the rationale could improve performance in continual learning. And indeed it did. So the idea here is not only to remember labels, but to remember rationales or strategies or salience maps. So you want to remember not only what the right answer was for a task, but how you found the answer, and make sure that when you replay those tasks to continue maintain your representation to be performant on those tasks, that you also replay the rationale and put a loss on the rationale. And this is where we begin to sort of get outside of that theoretical trade-off of, do we want to have interpretability or do we want to have performance? Because now the fact that we have interpretability allows us to have additional loss in our model, and that allows the model to ultimately perform better. So indeed, if you didn't remember the correct reason, and if you didn't have loss on your saliency map, you might forget the initial reason and lose performance. So the architecture is illustrated here. You would not only remember in your experience replay the original image and its label, but you would also remember the salience map or other structural explanation. You could also probably do this with textual explanation, but we've not looked into that. And when you go and replay the model, you have a loss on your saliency map as well as on your original remembered sample. So we looked at a number of different techniques, including GradCam and the others listed here, and all of them showed significant improvements. I'm just going to highlight one result chart, which shows, in general, we'd like to have models that were met the ceiling of joint optimization. That's the red cross in the upper right, and the gray slope descending down is the catastrophic forgetting of a fine-tuning algorithm on this standard ImageNet task that's split into 10 different groups. And you can see a number of different baseline techniques, Actually, the punchline here is this idea of adding XAI could be added to almost every existing continual learning approach. So all of the lines were baseline was the addition of this idea. So, this isn't the only solution to continual learning, but in nearly every technique we looked at, adding an XAI approach improved performance. and sort of added this boost of, if you're going to bother to remember something, you might as well remember your rationale and make sure that when you replay it, you can also perform, the rationale as well. Just like when my son has a test at school, in middle school, he has to show his work on his quizzes and his exams. He doesn't get full points if he doesn't show his work. And it's because with humans, and we argue with machines, if you learn to show your work and you remember the rationales, you'll do better and you'll generalize better in future conditions as well. We also showed in this work that the model could actually have a better grounding of the explanation, that the actual heat map was well aligned with human expectations, or sorry, the ground truth labels of the objects in the sea. So here's an example run of this. The upper row of images here are the baseline output of the baseline experience replay, and the bottom row with our remembering for the right reasons method. And you can see that, so you wanted to see basically the same heat map in every image. And with experience replay, after being distracted by all the other tasks that the model is learning, after the 11th task, it's forgotten the right label and it's looking at the wrong part of the image. But if you continue to provide loss on the rationale, it keeps focused on what's important in the image and continues to get the correct label, even though it actually got the incorrect label momentarily after task 5 in this example. Okay, so how much time do I have left? Hopefully another 10, 15 minutes. What time? I think we started 15 or 20 minutes late. Right?
Yes, so, and the next thing is a break, so.
Okay, I'm eating into your break, so maybe if people are upset about that, please ask questions and make me go faster. So now I want to pivot a little bit towards the justification side. Also remind, maybe do a little historical perspective on text-based justifications work that we did over the years. Anya Rohrbach, who's in the audience, was a lead on many of these projects. Lisa Hendricks was the leading grad student on this. And we looked at models for textual justification, and we called them visualizations, in contrast to just visual descriptions, which would be image captions, or class definitions, which would just be like Wikipedia entries. But visual explanations were essentially captions that were conditioned on a decision. So you would say, this is a cardinal because it has these properties. And these properties would be things that are visible in the image. So what type of bird is this? And you see, and so on and so forth. We also built a counterfactual pipeline, which could not only explain a decision, but explain why other classes were not actually suitable for the particular image in question. So this architecture would first predict the evidence for a certain category, ground that evidence using salience maps that were evaluated over specific regions of the image, and then construct a sentence that said why this actually wasn't an appropriate category to conclude here, because particular categorical evidence wasn't grounded in that image. So those are two historical lines of work that I think had somewhat impact. And recently we've brought them together in a system for autonomous driving that included both modularity and justification. This is work that was in collaboration with John Canny over the past few years. And again, we're going to leverage both salience visualizations, in this case, causal visualizations of both of model attention that we relate to human attention in similar scenarios, and textual justifications that we're going to use in reverse for model advice. So as in other applications that we've seen in this workshop and elsewhere in the literature, you can have saliency maps, you can have an autonomous driving as well, and you can relate it to what human drivers might be paying attention to, or human observers of driving might be paying attention to as they either drive or look at driving videos. And we relate that to specific object hypotheses, because obviously we have models of car identification and car tracking and detection of other signals or objects in the world. And we added to that a textual driving explanation or justification model, initially using label data where we had human annotators provide descriptions with an explanation. So for every frame in the video that was annotated, an annotator would give a description of what was happening and then an explanation for what a driving instructor might have said is a rationale for what's happening. And in our early work, we showed that having those additional losses also could improve performance in terms of driving prediction. But initially, we thought of this as just explanations, as maybe it would be interesting or feel like it was a more trustworthy system to see this textual generation. But in the end, that wasn't what was important, as we'll see in the following few slides. But just to recap that early work at ECCB 18, we had a very primitive autonomous driving controller, which would take frames and decide what direction to predict the steering wheel to go and what direction, how much to affect the acceleration. And then we would also output a textual description using an LSTM style model that was trained on the annotated rationales that I just described. So the model could predict a steering control and then also predict some text that described what the car was doing, and also an explanation that was consistent or a post hoc rationale for the model. Actually, in this work and in the other work of Jin-Kyu Kim and John Canny, it wasn't purely post hoc. The attention model was constrained to be causal, so that the model attended to the same regions in making its driving prediction and in making its explanation. And so we had results such as this, where the model could both output driving or predict driving controls and textual explanations. So what I think was most exciting in the more recent version of this work was pivoting it towards advice. I think the intuition I have is that when you build an explainable AI system, you have the ability to generate interpretable models. And the fact that you have those interpretable models allows you now to provide loss on those models. So you can actually tell the system what to do and like why it was right or why it was wrong, and give it that encouragement. And there's two different kinds of advice that we consider in these architectures: direct advice and contextual advice. So when you direct advice is right here, right now, let me tell you something that you should pay attention to. There's a pedestrian crossing the road and you might not have noticed it. Most interesting is contextual advice, is to take all of that corpus of here's what's happening and why, and turn it in reverse so that you can say, when this happens, then you should do this. And so ultimately, the ability to have an XAI system lets you build a hybrid quasi-rule-based and end-to-end trainable deep learning system. So the overall architecture that we explored, and this was in a 2020 CVPR paper, is shown here, where you have, this is the direct advice example, where you have a model that was trained to be able to provide textual advice, and then you prompt it with textual cues about things that it should pay attention to. Like, pay attention to this pedestrian in the crosswalk, and it does. The contextual version of this is perhaps the most exciting in the long term, which is if you take that description and think of it as having the two parts that I mentioned before, the explanation and the description, you can then drive that backwards as a rule, a condition to an action, and teach the model to internalize these rules from the training corpus. And so we had this overall architecture that would, in essence, say, I should slow down when the road is wet, or if I see a pedestrian crossing, I should stop. And it learned those behaviors from these additional textual explanations. You can look at the paper for the details, but in general, the explainable and advisable forms the baselines. All right, I'm really plowing into the break. I don't want to take too much more of your time, so I'm just going to spotlight the very latest work, including work we have at this conference on Friday at 10 a.m. So if you're interested in this, please go see Susie and Lisa's paper on guiding visual attention with language specification, which takes this general paradigm further towards advisable visual classification. Now, pivoting back from the driving domain to the more traditional fine-grained classification. And here we create very, very challenges, which are like, they're more philosophically ambiguous. Like, what is the, so here we have a data set, and I'll tell you the labels are 0 on the left and 1 on the right. But I actually had an underlying goal. This was just the data I happened to collect, on a Tuesday afternoon because I'm the naturalist on duty. But you don't know ahead of time, was the goal here to classify the background or the foreground? These are water birds and land birds, but actually I'd like to classify the water birds even when they're on land and vice versa, right? And if you have a very small training set, you can easily have this unintended correlation bias. And really, there's nothing you can do with traditional methods. They easily could overfit. Well, you could just step back and say, let's not train a model at all with a small bias training set. Let's fly the flag of foundation models and go use CLIP or other state-of-the-art models. And that works well. It's robust, and it won't get confused. At least not yet. I guess with models like CLIP and whatnot, you have to always check archive before you give a talk because you never know what results might have posted in the last 2 hours or something like that. But still, these foundation models don't solve all problems all the time, especially fine-grained problems. So we still would like to be able to kind of leverage a model that we do train ourselves, even on biased data. And the idea that we've explored is to use a device that constrains the attention of our fine-grained model. So as you can, here's the overall architecture of this GAL system, guiding visual attention with language specification. And you can ask the first authors what the joke is about the title when you're at their poster. And it essentially says, maybe it's cheating. It's saying, I have a training set. Let's also add some natural language to the training set. Like, let's let the person who collected that training data give us birds saying what the problem statement is. That, oh, I'm trying to recognize these birds, or I'm trying to recognize these environments. Just that phrasing is enough to get us out of this quandary. That's what you would do with a human being. If you said, here's some examples of birds, please find other birds. They wouldn't get confused by the spurious background condition. They might use it when it was relevant, but so the idea is to leverage the power of large-scale language models and the ability to tune fine-grained ConvNet models, and use the former for robustness and specifying what to pay attention to, and the latter for accuracy in terms of finding the specific features that are salient in an environment. This is our archive. As I said, it's also a paper on Friday. We run it on data sets such as water birds and show improved performance over all the baselines that we could consider. And essentially, you might think this is a very obvious idea. It really is. It's saying in most settings, you should consider the training data to be multimodal. The training data should have advice, which would almost be an inverse explanation. And you should tell the model what to pay attention to and make sure it does pay attention to the right things. So this is the harmonization of large-scale language models and CNNs. And there's a URL there if you're interested. A quick tease, we're also extending this from language to domain adaptation, but since I'm running out of time, I think I'm going to skip that. I'm going to just mention what I covered today were these architectures for salience and modularity, and having methods that were right for the right reasons and didn't have catastrophic forgetting in continual learning. We summarized textual justification models for fine-grained classification, how they can be used for advice and autonomous driving, and then this architecture for guiding attention with language specification. And with that, I'll be happy to take any questions. Thank you very much.
Just one side note, because of the setup, the audience here and Zoom do not hear each other. So just
Okay,
repeat
I'll
the
repeat
question.
for the
Thank you.
questions to come up.
Thanks a lot for this presentation. A lot of things, all the things that you said made great sense, and advisable co-access interpretation makes a lot of sense, including languages into for explaining English is very good. My question was perhaps using this for a different application. I was thinking like most of the explainable and interpretable models work for classification datasets. If I have a challenge, the point that you mentioned about catastrophic forgetting, this problem is valid for all other tasks also. Suppose, say, I'm using a master CNN to find people in images, and catastrophic forgetting is very much valid in that case also. Over time, with addition of data, suppose the model forgets masking instances on people, its IOU starts reducing on people. And the question is there a concept like, is there a way we can use this for that purpose, like understanding how to like, you know, measure the reduction in IOU for object masking tasks? Can we somehow use this for that? But it seems very relevant.
Yeah, I mean, I would think we can find an advisable AI paradigm for predicting segmentation masks by using language to describe parts of the image that were not covered correctly in a classification. The question, yeah, great.
But has this not?
Maybe we could, I think we should probably.
I have two questions.
Can you speak more loudly?
Yes. My first question is, you showed a couple of examples from visual language. So to what extent have these visual explanations like is it always necessary to have like a community of visual language to utilize explanations? Because from my experience working with that datasets, they're only helpful if I know to present in words or to explain to things like visually more. Would that have been considered? Well, essentially, our explanations only use words and find ways to use visual language.
Our explanations only useful for vision and language.
Can you
The
repeat
question
it?
was, are explanations only visual for, are explanations only useful for vision and language? I mean, you can also have explanations that are at the level of attributes or parts. You might call that language. Can you give me a non-language phenomena that you're interested in?
For example, if you want to get using the visual schemats for some
Audio is so bad here, I can't.
Yeah.
So if you could use these values without trying to explain in language what the explanation is getting at to a human business service or to an expert getting the models itself, would that be useful in this kind of help?
Yeah, it sounds. So you were describing a 3D task?
It can be any downstream task, but I'm wondering if it is necessary for the explanation to be interpretable in order to be useful.
Absolutely not. I don't think you have to have interpretability to be useful. I mean, I think it's a desirable characteristic, in my opinion, and one that if you use it in the right way, can lead to more improved performance through these ideas in advisable AI. But maybe we should talk more offline because I think I only heard half the questions.
My second question was, how do the explanations be shown to help incorporate that? For example,
You know, I actually just can't hear because it's garbled. The audio is garbled up here, unfortunately. So I'm going to have to.
Maybe you can actually come
Yeah, come up here and ask the question in this microphone.
Yeah, but it's true. We have been dealing with this the whole
Yeah.
day.
So my second question was, have these explanations been tested in corporate settings where human and an ML model are solving the tasks of the navigation or show a really nice example of providing training tools and self-driving? How do we evaluate the extent to which they help human in those scenarios?
Yeah, I love that question. I think that's a very much understudied area of work. So far, we've only been exploring how the human in the loop, in the sense of the person training the system or providing guidance for the system, can be improved. And I think the most exciting scenarios for the future, echoing actually ideas that I saw in another workshop earlier today about social interaction. I mean, probably the future of AI are highly social, highly interactive human AI teams, where the AI agents need to have explanations, and the humans need to be able to advise them on what they're doing. But that's still future work, at least from my group. Should we try one more question?
Yes, one more.
Maybe come up here and ask it.
Yes.
Hi, Professor. I'm Trevor Darrell from Columbia University. My question is for
Speak in the microphone. Sorry.
predicting the right thing for the right reason. Basically, you need the right specification for what is the right reason, right? Without that prior, you have no idea about the foreground or the background. I'm wondering how do we scale up this specification in more than large scale data set? Because it's hard to specify for individual images in a very large scale data set. Thank you.
Well, I think the cost of collecting rationales isn't that much higher than the cost of collecting labels in the first place. So I don't know that I have a good answer to your question outside of the realm of supervised learning. But within supervised learning, I feel like it's usually cost effective to collect, textual rationale or other markings on an image of what was supporting the label. So I think we should now have a break.
Okay, let's thank the speaker once more. Okay, thank you very much.